Hi everybody and welcome to Microfluidics 1. Today we will learn about electrokinetic effects. Let's start with a short example. On the right hand side you can see the results of an experiment. The left pictures depict a flow and the right pictures depict another one. At the top and the bottom of each picture, there is a wall and the liquid moves from the left to the right. And what you can see on the right-hand side should be familiar to you by now. It depicts the Hagen-Poiseuille flow velocity profile as a parabolic form. On the left pictures, you only see a straight line which slowly moves from the left to the right and gets more and more blurry because of diffusion effects. So far, you only discussed the Hagen-Poiseuille flow profiles. So how is it possible to move a liquid from the left to the right with an almost constant line as velocity profile? And to understand this, we need to understand electrokinetic effects. And the first part of this lecture today is that you will be able to name the different principles of electrokinetic transport. We will also learn about the basic models for electrical double layers. And finally, based on these 2 points, you will be able to explain the origin of electroosmotic flow, which is represented by this constant flow profile. To get to know the theory of electrokinetics, we prepared 4 videos. One is an introduction video and will introduce the concept of electrophoresis to you. In the second video, you will learn about electrical double layers. The third video will describe the impact of electrical double layers, which basically result in electroosmotic flows. And the final video will be an introduction to dielectrophoresis. In the lecture, we will cover 2 examples to deepen your knowledge within this topic. In general, you can state that electrokinetics describe kinetic effects induced by electric fields. And these kinetic effects can either be a liquid flow or particle movement. So now I want you to take a look at the right-hand side, because this is a picture that will come over and over again. Usually the black colored borders are electrodes and the blue colored area is a liquid. And the circles that are within this liquid are usually charged ions or particles. If you now apply a voltage on the electrodes, indicated by positive and negative signs, the particles will move in the respective direction. What is the resulting force at this point on a negatively charged particle? This force can be described and is given by electrodynamics. So it consists of the charge of the particle Q multiplied with the electric field E plus the velocity as cross product with the external magnetic field B. To make our lecture not too complicated, we will neglect in this lecture external and self-induced magnetic fields, meaning that the second part of the upper equation here will always be 0 for our analysis. This force can also be added to the Navier-Stokes equations. And this can be done by adding on the right-hand side a source term consisting of the charge density rho electric in our lecture times the electric field. So all the other terms should be known to you, the volume forces, the viscous terms, as well as the pressure gradients within your liquid. Very crucial for this lecture is the Poisson equation described here. So on the left-hand side, you have a delta phi electric, which equals to the minus charge density divided by the permittivity of the vacuum times the permittivity of your liquid. And in this case, we are going to do it the other way around. So we are going to look where these parts come from, where does the left part come from, where does the right part come from, so that you understand which assumptions we took to get to the Poisson equation. And we start with the left-hand side. So in electrostatics, you probably already know that electric fields can be described by a potential, which is phi electric. And this potential can be basically described by the electric field, which equals to minus the gradient of your potential. And if we now build the gradient of this electric field, we get the gradient to the square of the electric potential, and this results in our left-hand side of the Poisson equation. For the right-hand side, we need to know the Gauss law, which is depicted in this equation. So you have a gradient of a displacement field, electric displacement field, which equals to the charge density. And if you remember electrostatics, you know that the displacement field consists of an electric field in times the vacuum permittivity plus the polarization of your medium. And on the right-hand side, you can see that what polarization means again. So if you have bipolar molecules like in H2O, they will change their direction according to the applied electric field. So the negative charged parts of the molecule will point in direction of the positive charged electrode and vice versa. And this positioning of the molecules will lead to the creation of an electric field, which is described by the polarization P. In our case, for this lecture, we will only look into liquids and isotropic solids, and that's why you can simplify the displacement field described in this equation. So the polarization can be replaced by a vacuum permittivity times C times the electric field, because the electric field is then proportional to the polarization P, and you end up with this equation for the electric displacement field. And finally, if you now get the gradient of the electric field, you will get the gradient of the displacement field divided by those two factors, and you end up with the result of the right-hand side of the Poisson equation. So if we now put both calculations into one equation, you will see that on the left-hand side, you have the electrostatic potential derived from the potential equation of electrostatics. And on the right-hand side, you have the result of the Gauss law which includes some assumptions like a proportionality between the polarization and the electrostatic field. In general, it's possible that bipolar liquids form layers around your ions. So if we take water with H2O and a negatively charged particle, the H atoms will build a layer around your negatively charged particle. However, this will not change the total charge of your complex. So the total charge will remain positive and your particle will be attracted to the positively charged electrode. So that's it with a very superficial overview on the fundamentals that we require today. But now let's start with electrokinetics. And to do so, we will start with electrophoresis, which is obviously the easiest electrokinetic effect. And electrophoresis describes the movement of charged particles through stationary liquid induced by electric field. And that's what's depicted on the right-hand side. So you have negatively charged particles that are attracted by a positively charged electrode. If we now get a closer look on one of these negatively charged particles, you can see that there are two forces acting on it. One force is the electric force, and another force is the drag force, so the friction forces between the liquid and the particle. And you should by now be able to describe both of these forces. So the electric force, as seen at the start of this lecture, can be described by the charge of the particle times the electric field. And the charge of the particle depends on the valence number Z and the elementary charge E, which is a constant. The drag force, on the other hand, can be, for a spherical particle, be described by this equation here. So it's equal to -6p eta, the viscosity, times the radius of your particle, times the velocity of your movement. So if your particle doesn't move, there's obviously no friction force. And if you now want to get the velocity of your particle, you can just do the force balance between the drag force and the electric force. And you then will get a value for the velocity of your particle that depends on the electric field E and the so-called ionic mobility, mu ion in this case. And as you can see, if you have a closer look on the parameters, the higher the valence number, so the higher the charge of your particle, the faster the velocity will be. And on the other side, the higher the viscosity of your liquid and the bigger the particle, so the bigger the radius of the particle, the lower your velocity will become. And that's for sure. If there are more friction forces acting on the particle, it will move slower through your liquid.